Hey everyone, I'm Martin Olarte, and in this video, I'll be presenting our mini project for CMSC 197 machine learning entitled Cervix Spine Fracture Classifier using enhanced cutting edge detection and support vector machine. In this presentation, we'll be discussing the introduction, the methodology, the results and discussion, the conclusions, and recommendations for this mini project. This mini project revolves around the cervical spine, commonly referred to as the neck region, consists of 7 bones known as the vertebrae that supports and connect the head to the shoulder. The Radiological Society of North America in 2022 conducted an AI challenge that aims to quickly detect and determine the location of vertebral fractures through the development of machine learning models. Cervical spine fractures, which can occur due to high-energy trauma or shock, can be evaluated using plain X-rays or CT scans. However, only 25 to 32% of radiographically identified cervical spine fractures are clinically diagnosed. Hence, the main objective of this mini project is to develop a binary classification model using enhanced cutting edge detection or ECED and support vector machine SVM to classify whether a cervical X-ray scan is fractured or not. Specifically, we have the specific objectives, that is to create the different models using different SVM kernels, these different metrics in order to compare the performance of the three models and then to compare the runtimes of the said models. For our methodology, it consists of three major parts. First, we have processed the image, so that's the image preprocessing. Then we'll process the image data using the image data preprocessing. And finally, the model will be trained and evaluated. We have downloaded 4,600 images from Kaggle, wherein 4,200 images are for training dataset and 400 images are used for testing, wherein each datasets are equally divided into the normal and fractured images. After downloading, the images were named for ease of processing. And then each image undergone an image feature enhancement and selection using these three main parts as indicated in the figure. First, the image pre-feature enhancement, then the image feature enhancement, and then finally the image feature selection, specifically using cutting edge detection using the image's median value. Then after the image was processed, the processed image was converted into the image matrix, which we'll be using in the data frame later on. Then we have labeled each of the processed images as following. For normal, it was labeled as 0. For fractured, it was labeled as 1. And then for model training, we have created three models, one of which is a linear SVM and two are nonlinear SVM. Model A is the linear SVM, Model B is a nonlinear SVM using radial basis function kernel, and Model C is a nonlinear SVM also, but it uses the polynomial kernel or polykernel. For the evaluation, we have these three main parts, which is the confusion matrices, classification report scores, such as the accuracy, precision, recall, and F1 scores, AUC, ROC, and we also have taken note of the runtime in the evaluation part for each of the models. Proceeding with the results and discussions. First, we have here the confusion matrix of Model A. As we can see here, 175 out of 200 normal images were correctly labeled, and 180 out of 200 fractured images are correctly labeled. For Model B, we can see a higher score than Model A, wherein 198 out of 200 normal images are correctly labeled, and 189 out of 200 fractured images are correctly labeled. Proceeding with Model C, we can see here that 4 out of 200 normal images are correctly labeled, and all fractured images are correctly labeled. With this, we can see at this table that Model B is the highest performing model in terms of its accuracy, precision, and F1 scores. However, we should take note that even though Model C scored a 100% recall, if we go back to our confusion matrix, we can see that the Model C almost predicted every images as fractured images except for the 4 normal images that it has predicted correctly, meaning that even though its recall is 100%, its performance is affected by its precision having only 50% and the accuracy as well is 51%. Hence, the F1 score is the lowest among the models. However, we should also take note that this might be because of the unoptimized parameters used for our models. Proceeding with the AUC ROC curves. In this graph, we can see that Model B covers around 99.78% of the area under the curve, and while Model A covers 95.97%, and finally, the worst performing model, Model C, only covers 89.11%. In terms of runtime, we can see that Model A is the fastest. It was able to classify all 400 test images in merely 135.45 seconds, meaning it would classify at least 3 images per second. For our conclusions, The computer vision techniques have been successful in enhancing the scans, as we can see on the performance results, wherein Model B performs the best and Model C performs the worst. However, we should take note that Model A is the fastest, whereas Model B is the slowest. With that, we can say that Model A could be used in emergency situations, and Model B could be used in situations where accuracy rather than the runtime is needed. For our recommendations. For our first recommendation, we recommend that the pre-processing parameters used could be adjusted. For example, in the enhanced scanning edge detection, we could use the mean values of the image rather than the median, or even the 23 percentile or 70 percentile M-test, whether this affects the scores of the model. Next is to use a grid search to find the optimal hyperparameters, not just for the linear SVM and the RBF, but also to the polynomial kernel SVM. And then finally, the models could be deployed in a web or mobile application. That is all for this presentation. Thank you for listening, and any questions regarding this mini project can send me an email as presented in the screen.